Okay, a student in Google Meet, can you see my PowerPoint in slideshow? Okay, I already switched it to slideshow, but I don't know why it does not show through the screen. Okay, I think now should be okay. Okay, today I will start another topic, okay, which is about CMOS power dissipation. Okay, this topic is also quite important. Okay, the performance of the CMOS circuit, we have to evaluate it based on this power dissipation. Okay, right. What is the outline for this CMOS power dissipation? Okay, this is the outline. The motivations to determine the power dissipation. Okay, since power dissipation is one of the main factor, okay, to the performance of the CMOS circuit. So it is quite important for the designer, okay, to estimate and to determine the power dissipation. The power dissipations, of course, must be low, okay, must be low. We have to ensure that it is not high, okay, in the CMOS device, okay. There will be some consequences that will be covered later. The consequences will be mentioned. Okay, if there is high power dissipations, then what will happen? Okay, and then so that brings to these motivations. Okay, and the source of power dissipations. Okay, power dissipations have many types. Okay, there is a static power dissipations and dynamic power dissipation. Okay, these two power dissipations are caused by different source. Okay, so later I will mention about that. What are the source that cause these two power dissipation? Okay, after that, I will also mention so what are the technique that can use to reduce the power dissipation. Okay, so all this will be covered under this topic. Okay, so as an introductions, okay, the numbers of battery power handheld applications, okay, for example, the mobile phones and the laptop computer is steadily increasing and more functions are integrated into the system. Thus, this is one of the driving force for analysis of the mechanism of power dissipations and power reductions technique. The need of incredible power dissipations of microprocessor where heat removal and current delivery are very hard and expensive to achieve. Okay, so power dissipations, we have to make sure that it is as low as possible. Okay, if a device dissipate high power, then we have to find a solutions to reduce it. Okay, the solutions to reduce it will also require some cost. Okay, so the cost will be expensive as well. Okay, so mm, this is the introductions. Okay, power dissipations affect, okay, many ways. Okay, uh, the um, it will affect the performance. Okay, it will affect the performance, reliability, packaging, portability, and cost. Okay, so cost will be increased. Okay, if power dissipation is high. Okay, and then the cost will include the cost of cooling. Okay, to reduce the power dissipation. Okay, and about performance and reliability. Okay, if a device dissipate high power, so it means that it will reduce the lifetime of the device. Okay, so means if the device has high power dissipations, means it is not reliable. Okay, and then could also affect low performance. Okay, and packaging portability, these are all related. Okay, if we want to cool down the device, okay, then maybe the structure or the form how the device package will be different. Okay, CMOS technology is scaling to meet the performance, cost reductions, power requirement. Okay, so you see the graph here. Okay, all these are the digital system. Okay, digital system with chip, and then with the performance. Okay, the performance increases. Okay, with high frequency and the use of high power. Okay, so when they when the increase of high power use, okay, means there is an increase of the performance of the digital system. Okay, and at the same time, okay, another issue that can also cause, which is uh, the digital system will dissipate high power. Okay, so all the factors here mentioned are all related. Okay, okay, reliability and cooling costs. Okay, high power dissipations will cause high temperature. Okay, this high temperature means high temperature within the device. Okay, and when there is a high temperature, means that it will brings to malfunctions of the device. Okay, and high performance microprocessor will require about 50 watt. Okay, and the packaging cost and cooling costs. Okay, with high power dissipations, then the cost that will induce to be higher, because the cost will include the packaging cost and the cooling cost. Okay, the cooling cost of course is to account for the fan. Okay, maybe the fan can use to cool down the power, to cool down the device to reduce the power dissipation. Okay, so this is the cost that have to consider. Okay, to ensure the reliability of the device. And then the power supply. Okay, power supply rails have high transient current. Okay, okay, this one will have uh, some uh, influence. Okay, it will affect the performance. Okay, the performance and the power dissipation. And then in terms of environmental concern, okay, the power dissipations is caused by electricity. Okay, so electricity generations will cause air pollutions and consumptions of energy sources. Power dissipation in CMOS is caused by many different sources. Okay, and then they can be classified into two. Okay, static dissipations and dynamic dissipations. Okay, for static dissipations, it is caused by the subthreshold current, okay, and gate linkage, reverse bias diode linkage, and condension current. Okay, so what are these? It will be mentioned. Okay, and also the dynamic power dissipations is caused by the capacitive switching, gate linkage, and the short circuit. Okay, short circuit is where the PMOS and NMOS are partially on and off. Then there will be a path, a conducting path from the PMOS to NMOS. Okay, so there is a short circuit. Okay, when they are uh, in saturation mode. Okay, for both transistors. Okay. Okay, now I will first cover on static power dissipations. The static power dissipations become an issue when the circuit are inactive or in a power down mode. It means that is when there is no activity in the circuit and they are all biased to a specific state. Okay, so by the means here, okay, static means that it happens. Okay, it happens when the circuit is off. Okay, it's inactive. Okay, so this is how you can differentiate between static and dynamic power dissipations. Static power dissipations occur when the circuits are off or inactive. Okay, and then the cause of these static power dissipations are from the subthreshold linkage through off transistor. Okay, and also gate linkage through gate dielectric, junction linkage from source to drain, not to drain, is source or either source or drain diffusions. Okay, even though the circuit are off, okay, there are also some power dissipations. The power dissipations maybe is not high. The amount may be in micron or milliwatt. Okay, but we still have to consider it. Okay, because if a power dissipations for a transistor is very small, okay, if it all the power dissipations for all the transistors are accumulate, okay, then there will be quite high power dissipations. So this static power dissipations also have to consider. Okay, the cause is from these causes. Okay, they are due to the linkage that occur within the transistor. Okay, due to the necessary downscaling of threshold voltages, the subthreshold linkage is becoming more and more pronounced. Below the threshold voltage in weak inversion, the transistors are not completely off. The subthreshold current has a strong dependence on the threshold voltage. Okay, the meanings here is, okay, for a transistor that is having an input voltage below the threshold voltage. Okay, the for example the NMOS. Okay, NMOS, when the input voltage is low, which is below the threshold voltage, okay, um, there will still be power dissipation. Okay, the NMOS, even though it is in cut off, but it is not completely off. Okay, okay, I want to write something here. Okay, just now I tried to write, I cannot. Okay, so this is the condition where input voltage is below the threshold voltage. Okay, in real case, transistors are not completely off. Okay, it will cause static power dissipation. Okay. Okay, static power dissipation is caused by the linkage through the gate, source, and drain terminal. Okay, and also the subthreshold. Okay, subthreshold here is on about the subthreshold current. Okay, okay here is for you to see the conditions, okay, or the selections of the threshold voltage, okay, will actually will cause the amount, okay, will cause the amounts of the power static power dissipation, okay. And next is dynamic power dissipation. Okay, it occurs when the circuit is operational. Okay, for example, the circuit is performing some tasks on some data. Okay, so this one, okay, you must remember that dynamic power dissipations occurs when the circuit is on. Okay, it is meant by the circuit when it is on. Okay, further subdivided into three mechanisms: switch, short circuit, and glitch power dissipations. All of them depends on the activity, timing, output capacitance, and supplies voltage of the circuit. Okay, so since the dynamic power dissipations occurs when the circuit is on, so means that the circuit is in activity, is operated, and then it is with several activity. Okay, so all the activity will involve switching, okay, and also timing, and then transmissions, okay, and then when it is on, the circuit is on, they must also have a supply voltage, okay, and also in that transistor circuit, okay, the output, okay, also has this load capacitance. Okay, so here mentions output capacitance because they are capacitance, okay, at each output of a transistor. So it will also dissipate power. Okay, the repeated charging and discharging of the output load capacitance as switch gate is necessary to transmit informations in CMOS circuit. The dynamic power dissipations of a CMOS circuit can be represented as P equals to F, okay, F C V D D squared. Okay, F is mean by the frequency. Okay, here mentioned is a clock frequency. Clock frequency determines the speed of switching. Okay, and the C here means the output capacitance. Okay, and VDD is the supply power. Not power, is voltage, supplies voltage. Okay, so based on the formulas given here, we can actually know the dynamic power dissipations is caused by the clock frequency, okay, and the output capacitance and the supply voltage. Okay, and also other terms here, okay, this is frequency, this is short circuit current, okay, and the supplies voltage. Okay, this term itself is actually means the short circuit um, current that cause to power dissipation. Okay, sorry, okay, I accidentally clicked. Okay, short circuit current that cause power dissipation. Okay, and another term here, this term, okay, is the power dissipations that caused by linkage current. Okay, there is a current here is caused by the linkage current in a transistor. Okay, so this one you have to know. Okay, you must make sure that you understand what is meant by this formula here. Okay, so through this formula, okay, it also means that the circuit is uh, in operation. Okay, and then there are some of the dynamic power dissipations occur. Okay, now I go to the next slide. Okay, using a lower VDD is an effective way to reduce the dynamic power dissipations, since first term, okay, is proportional to the square of VDD. Okay, so this one looks like an I. Okay, it is actually means the first term. Okay, first term of this one. This one is the first term. Okay, the statement just now is actually refer to this term. Okay, you can see the relationship between VDD and the power dissipations. When the power supply is high, okay, the supply voltage is caused by the supply voltage. Okay, so when it is high, power dissipations will also be high. So it is important to ensure that a lower VDD, okay, so that the power dissipations can be reduced. Okay, and then the short circuit and the linkage power dissipations are also strongly dependent on VDD. Okay, however, using a lower VDD degrades a performance. Okay, so you see the trade-off here. Okay, okay, higher power use will increase the performance, but we cannot use a high power supply, okay, because it will cause high dissipations. So the choice of the supply's voltage is also quite important. Okay, we want to achieve low power dissipations, and also at the same time we want to ensure the performance is well achieved. Okay, here there is a definition for a short circuit current. Okay, short circuit currents means while both PMOS and NMOS stacks are partially on. Okay, there is a diagram here which I can show you, but okay, not in this slide. Okay, okay, I will show later with a diagram. Okay, in the next few slides. Yeah, so I will cover this first. Okay, total power consumption. So this total power consumption is the summations of dynamic power and static power contribute the total power, which is defined as P total plus dynamic power dissipation plus uh, the static power dissipations. Okay, total power equals to the summations of the dynamic power dissipations and static power dissipation. And this dynamic power dissipations is caused by this switching. Okay, this switching power is actually this one, C FC VDD square. Okay, and then this is a short circuit power. This is the F I short and VDD. Okay, and there is also the linkage power, but it is not shown here. Okay, we can also include the power linkage. Okay, for static power dissipations, so you see here they are the linkage current. Okay, this is the subthreshold linkage current. Okay, and this is the linkage current, okay, of the gate. So means the gate linkage current. Okay, and this is the junction linkage current, and this is the condension current. Okay, this have to be multiplied with the supply voltage. Okay, so I will further elaborate on static power consumptions. Okay, so just now I just mentioned static power consumption is caused by some of the current. Okay, the currents are the linkage current. Okay, here there are some of the descriptions about what is linkage current. Okay, the current we sometimes call it static current. Okay, for the uh, linkage current or for the current that cause static power consumptions. Okay, it is sometimes called as static current. In CMOS, there is no static current as long as uh, V in is below the threshold voltage. Okay, or V in is above the VDD plus the threshold voltage. Okay, so this one there's no loading static current as long as V in is below the threshold voltage. Okay, so these statements, this statement means static current is not a linkage current. Okay, if just now I mentioned it wrongly, so this one it should be the correct one. Okay, static current is not linkage current. Okay, linkage current. Okay, linkage current is determined by the off transistor. Okay, it is influenced by the transistor with supply voltage, transistor threshold voltages. Okay, and then here there are two conditions. Okay, two conditions here. One is the linkage currents in NMOS. Okay, this occur when the input voltage is below the threshold voltage. Means that this is on, this is off. Okay, when the NMOS is off, there is a linkage current in this transistor. Okay, so and then when the input voltage is high, VDD. Okay, for this case, this diagram. Okay, the PMOS will be off. Okay, then this is on. Okay, when the PMOS is off, this is off. Okay, when PMOS is off, then there is a linkage current in the PMOS transistor. Okay, so all the linkage currents here, there are 4 different linkage current. Okay, and just now already stated the 4 is the gate linkage current, junction linkage current, and what else? Subthreshold linkage current. Okay. Okay, and then there is another one. Another one is you have to check here is the condension current if you refer to this formula. Static power is consumed even when a chip is not switching. CMOS has replaced NMOS processors because condension current inherent to NMOS logic limited the numbers of transistors that could be integrated on one chip. Static CMOS gate have no condension current. Okay, so this one you have to take note. Okay, and figure 2.19 illustrate the static power arises from subthreshold connections between source and drain. gate linkage from the gate to body, and junctions linkage from source to body and drain to body for equations 5.12. Okay, equation 5.12 is the one that I show you. Okay, this one. Okay, it refers to this formula. Okay, because subthreshold linkage is usually the dominant source of static power, other techniques for linkage reductions are explored, including multiple threshold voltages, variable threshold voltages, and stake forcing. Okay, this diagram shows what is all the linkage current. Okay, so you see here, this is a CMOS inverter. Okay, for example, this NMOS is off. Okay, and then there is a gate linkage. Okay, gate linkage occur from the gate to the substrate, okay, of the transistor. Okay, and also there is a subthreshold current. Subthreshold current is occur from source to drain or the drain to source. In this case, it is from the drain to source. Okay, and also at the output here, okay, at the output, there is a some drain junctions linkage. Okay, so all these linkage current, when we multiply with the VDD, it will uh, cause the it will determine, okay, it can determines the static power dissipations. Okay, and then there is another diagram here, also show the same thing. Okay, it shows the side wheel of the transistor. Okay, and then this side wheel, you can see the directions of the currents flow, okay, for each of the linkage current. Okay, so in this, you see that this is the linkage current from the gate to the substrate. Okay, and then the subthreshold. I subthreshold is the subthreshold linkage current. Okay, and then I junction. I junction is the junction linkage current. Okay, the linkage is happen from the drain terminal to the substrate. Okay, okay, subthreshold current is the dominant factor among all the others linkage current. Okay, all increases exponentially with temperature. Okay, just now the diagram mentions on the subthreshold linkage current and gate linkage and junction linkage. Here are all the definitions for all the linkage current. Okay, for subthreshold linkage current, okay, we also can call it as a subthreshold conduction. Okay, it is caused by thermal emissions of carrier over the potentials barrier set by the threshold. Okay, and then gate linkage is a quantum mechanical effect caused by tunneling through the extremely thin gate dielectric. Okay, what is meant by tunneling here is the effect of the carrier crossing a thin barrier and result in linkage current through the gate. Okay, and the junction linkage is caused by current through the PN junctions between the source and drain diffusions and the body. Okay, so you see the 2D 2D diagram of the transistor or of the CMOS transistor. Okay, uh, you can see that there are source and drain diffusions, and source and drain diffusions and the body in between, they can create a PN junction or a diode. Okay, so that also there is a linkage current okay, from one terminals to the body. The process has two threshold voltages and two oxide thickness. Okay, two threshold voltage here. Why? Because there is a PMOS and NMOS. So the threshold is voltage is for these two transistor. Okay, and then two oxide thickness. This oxide thickness is the thickness under the gate, the thickness of the oxide under the gate. Okay, I refer back to this diagram. Okay, you see here, this is gate. Okay, this is gate. And in between the gate and the body, there is an oxide layer here. Okay, this oxide layer is very thin. Okay, even though it is thin, but some of the carriers still can transmit. Okay, let me see again. Okay, not transmit. Okay, there is some carrier emissions. Okay, if there are a certain potential achieved. Okay, but anyhow, what I want to mention here is the thickness of the oxide that is referred to this one. Okay, okay, and just now mentioned about the thickness of the oxide, so it will cause some linkage current. Okay, and then the subthreshold linkage. Okay, this is about the values. Okay, for different level of the threshold voltage. Okay, for subthreshold linkage. Okay, the currents can be in 20 nanoampere, okay, per micrometer for low threshold voltage. Okay, and then the subthreshold linkage is around 0.02 nanoampere over the micrometer for high threshold voltage. Okay, and then the gate linkage. Gate linkage, if the oxide is thin, okay, the gate linkage will achieve as high as a 3 nanoampere. Okay, this is quite high if compared with the thick oxide. Okay, the gate linkage only 0.002 nanoampere if a thick oxide is used. Okay, so you see the relationship here. The linkage current between linkage current and the oxide thickness and the threshold voltage. Memory use low linkage transistor everywhere. Gate use low linkage transistor on 80% of logic. Okay, so you see the linkage current is very small. Even though it is small, but it's still critical. Okay, we have to ensure that the linkage currents will not increase because some of the devices, they need low linkage transistors. Okay, for example, memory use low linkage transistor. Okay, so next I will mention on dynamic power dissipations. Okay, this slide, okay, is about the derivations of the formula, okay, to determine the dynamic power dissipations. Okay, so given here, case 1, okay, when input is at logic 1, not logic 1, is at logic 0, power dissipations in PMOS is P equals to I multiplied with voltage. Okay, so this one is the current, okay, current and the voltage. Okay, current is the current from the source to drain, okay, across the transistor, okay, in this transistor through the channels. Okay, and then the V here is the voltage drop, across the transistor. Okay, it is defined in this way. The current and voltages are related by current equals to C multiply dV over dt. Okay, here CL is the output capacitance. Okay, and then here is the potential difference. They are potential different. Okay, it means that when there is a current flow, okay, flow from the supply's voltage to the output. Okay, when this is on, okay, output will be high. So here we'll charge up. Okay, currents flow through to the capacitance and there is a charge up. Okay, there is a charging process here. Okay, and then the potential here, okay, will change from time to time. Okay, so this is related by this formula. Okay, similarly, energy dissipations in the PMOS, okay, is equals to 1 over 2 CL multiply VDD square. Okay, this is the formula where we can calculate the energy dissipations in the PMOS. Okay, in case 2 is when the input is high and the output is low. Okay, these power dissipations occur in NMOS. Okay, during switching, all the energy stored in the load capacitance is dissipated in the NMOS device. Is conducting and PMOS is in cutoff mode. The energy dissipations in the NMOS inverter can be written as ET equals to FCL VDD square. Okay, this is where all the energy stored in the load capacitance is dissipated in the NMOS device. Okay, so there are two. Okay, there are two energy dissipations formula. Okay, for the respective NMOS and PMOS. Power dissipations in terms of frequency. Okay, it is written as ET equals to FCL VDD square. Okay, this is for the NMOS. Okay, this is for the NMOS. Above equations shows that the power dissipations in the CMOS inverter is directly proportional to the switching frequency and the VDD square. Okay, just now I show you the formula with the switching power. Okay, this is FC VDD square and plus FCL VDD. Is it C? Okay. Okay, there is a formula. Okay, just now I show you in equation 5.11, 5.11, 5.2. Okay, yes, it's a 5.11. Okay, I refer to this one. Okay, I mentions here. Okay. Okay, the relationship you can know CMOS inverter is directly proportional to the switching frequency and VDD square. Okay, F here, okay, in dynamic power dissipations, frequency, okay, have the importance effect, okay, to the power dissipations. Okay, so the frequency here is mean by the clock frequency. Okay, and then this clock frequency determine the switching frequency. Okay, this is switching frequency. Okay, this is clock frequency, and then here there is a factor here. We call it as the activity factor. Okay, when activity factor multiply with the clock frequency, then it will determine the rate of the switching. Okay, the how fast or how slow the switching occur. Okay, so FSW is the switching frequency. Okay, if the signal is a clock, okay, it means the activity factor is 1. If the signal switches 1 per cycle, okay, and the activity factors will be half. Okay, and then the memory array, okay, the activity factor is 0.05. Okay, so uh, for different applications, the activity factors will be different. Okay. Okay, again, you see here, this is the formula of the dynamic power dissipations. Okay, this is defined here. Okay, low power design involves considering and reducing each of the terms in switching power. As VDD is a quadratic terms, it is good to select the minimum VDD that can support the required frequency of operations. Okay, likewise, we choose the lowest frequency of operations that achieve the desired end performance. Okay, so the choice of the frequency is also important. Okay, the clock frequency, because if we want to use a very high clock frequency, it will cause an increasing power dissipation. Okay, so it will affect the performance. So the frequency cannot be too high. Okay, not too low. Okay, if too low, then means the switching frequency is also will be low. Okay, if you want to have a fast switching speed, okay, then the clock frequency we have to choose it appropriately. Power as functions of frequency. Okay, this graph is plot, okay, with power dissipations versus the frequency. Okay, you can see that when the frequency increase, okay, this frequency is the operating frequency, or maybe we can consider it as the clock frequency. Okay, this is clock frequency. Okay, same as the operating frequency. So when it is increasing, then the power dissipations also will be increased. Okay, you see the curve here, it shows that they are proportional. Okay, the curve, there are different line of the curve here. Okay, all these line are for different supplies voltage. Okay, the lowest supply voltages is 0.35 volt. Okay, highest is 1.2 volt. Okay, when a highest supply voltage is used, you see the curve here. Okay, the power dissipation is higher, okay, than the one for the line with a 0.35 volt supply voltage. Okay, and then all of them, okay, they have increased power dissipations when the frequency is increased. Okay, dynamic power dissipations just now mentioned, okay, it is caused by the switching power, and then the short circuit power. Okay, and also another one is what is okay, I forget already. Okay, just now remember, now I forget. Okay, there are three. Okay, so this is the short circuit power dissipation. Okay, I see the time is almost 3 now, and I feel like to take a break now, and then only later I continue with this one. Okay, maybe we take a break now. Okay, a 10 minutes break. After that, I come back. Okay, I will continue my lecture. Okay, I see that I still have a few more slides. Okay, I can cover all the slides today. Okay, and maybe we can end the class early today because I see that the slide that I have to cover is only 6 to 7 slides. Okay, so I think I'm going to cover all today within this half an hour. So means by 4, maybe I can cover all. So if I cover all, then we can dismiss early. Okay, now I will continue with a short circuit power dissipation. Okay, assume the inverter drive a 150 femtofarad capacitor at 1 gigahertz. When the input voltage rises, the PMOS starts to turn off. And there is a small bit of a current while the partially on PMOS fight against the NMOS. This is called short circuit current. Okay, so here there is a diagram here given with the input from low to high. Okay, when the input is low, okay, the PMOS is on and NMOS is off. Okay, and when the input voltage is increased, okay, at this region where the input voltage is increased, okay, the PMOS will be partially on and NMOS partially off. Okay, so here there are some conductions occur. Conductions means that there is a current flow, okay, but the current is very small, okay, the amount is very small. Okay, and then in this condition where the PMOS is partially on, NMOS is partially off. When I say NMOS is partially off, it also means that it is partially on. Okay, so when both transistors are partially on, so there will be a current flow from the supply voltage to the ground. So in this case, we call it as a short circuit condition. Okay, and there is a short circuit current. Okay, finite slope of the input signal causes a direct current path between the VDD and ground for a short period of time during switching when both the NMOS and PMOS transistors are conducting. Okay, so this is the definitions for short circuit current in this CMOS inverter. Okay, short circuit current cause the dynamic power dissipations. Okay, power dissipations has become a significant factors for recent IC, the integrated circuit. Not sorry, it's not factor. Okay, it's a elements. Okay, it's a significant elements that have to consider for recent IC. Okay, there is a large and growing class of applications where power reductions is critical. Okay, not speed. Higher power consumptions leads to shorter battery life. Okay, and higher on-chip temperature. Okay, higher on-chip temperature so will cause a reduced operating life of the chip. Okay, this um, this is not only applied to chip, okay, it is also applied to any other digital system device, okay, for example, maybe power bank, okay, or your mobile phone, okay. Our mobile phone, we cannot make it high temperature all the time, means that it cannot be under high temperature all the time, okay. If the mobile phone is under high temperature all the time, means that the lifetime, the phone lifetime, okay, will reduce, okay. So this one is applied to the chip, okay, also with the same concept, okay. um, so you need to remember higher power dissipations will cause a shorter battery life, okay. Why is a shorter battery life? Because of the high temperature that cause, okay, that are dissipated, okay, in the devices, okay. The temperature will cause the breakdown of the functions of the device, okay. Okay, why average power or energy reductions? Okay, there are some of the reason here why we need to reduce power dissipations. Okay, the reasons are to increase battery lifetime, to enhance noise margin, to reduce energy costs, to reduce use of natural resources, and to reduce system reliability. Okay, so these are the 5 reasons. Okay, need for low power VLSI chip. Okay, in a VLSI chip that has 100,000 transistor, okay, even though one transistor they dissipate a small amounts of power dissipations, but when we uh, consider for the 100,000 or thousand of transistor in a VLSI chip, okay, the power dissipations can be high, okay. The emergence of the battery power handheld devices such as mobile phone and laptop computers has called for low power operations. Power dissipations was neglected due to low device density and low operating frequency. Okay, this was last time, okay, when the chip that are produced with a low density of transistor. Okay, when the numbers of transistor are low, okay, the chip, okay, will not dissipate high power, okay. But now the power dissipations cannot neglect. We cannot neglect it. Okay, it is quite important issue. Okay, uh, now we have to consider the power dissipations because uh, high device density, high operating frequency, proliferations of portables, consumer electronics, concern on environments and energy sources. Okay. Okay, according to Moore's law, the transistor on lead microprocessor double every 2 years. Hence, a die size grows by 14% to satisfy Moore's law. Higher operating frequency was used in the chip and the power dissipation continues to increase. Power density is too high to keep the junctions at low temperature. Okay, when the numbers of transistor double every year, and then the size of the chip is getting smaller with increasing numbers of transistor, the dissipations, high power dissipations, we cannot avoid. Okay, but we have to find a way to reduce it. Okay, some of the techniques that we can consider, okay, to reduce the power dissipations when design the low power device, okay, or low power circuit of the device. Okay, To reduce the dynamic power dissipations, okay, some of the technique that we can use, okay, you see here there are four technique. This is to control the clock gating. Okay, this is the activity factors. Okay, activity factors indicates the activities of that device. Okay, when the device is in active mode, okay, means that there is a switching operation. Okay, so when the transistor is not operated, means it is not on. Okay, we can put the device under sleep mode. Okay, sleep mode can help to prevent any power dissipations. Okay, this is through the manipulations of the activity factors here. Okay, and capacitance is actually the load capacitance. Okay, not only load capacitance, there is also some other capacitance that have to consider. Okay, this capacitance can be the capacitance caused by the wire. Okay, you see here the wire. Okay, um, the length of the wire used is also critical. Okay, when longer wire use, okay, the power dissipations also will be high. Okay, so shorter wires is better. Okay, it can ensure higher speed of signal transmissions as well as lower power dissipations. Okay, and then the supplies voltage. Okay, supplies voltage is to select the lowest suitable voltage. Okay, lowest here you must understand that not the lowest is the better. Okay, here means is the lowest suitable. Okay, just now I mentioned if the supplies voltage is very low, the performance of the devices will not be good. Okay, so cannot choose very low supplies voltage. Okay, the lowest here is actually means the lowest suitable, so not too low, not too high, but the suitable one. Okay, and then the frequency here, frequency is the clock frequency. Okay, must choose a lowest one. Okay, not too high. Okay, because it will cause high frequency. Okay, how do we know all this can actually help to reduce the power dissipations, the dynamic power dissipations? You can always refer back to the formula here. Okay, this formula uh, show the relationship. Okay, so whichever uh, any of the elements here that we can actually adjust, like for example the supplies voltage, when we adjust the values of the supplies voltage, then the dynamic power dissipations we also can adjust. Okay, we can reduce. Okay, and then for the static power dissipations, okay, static power dissipations also there are some technique that can be used to reduce it. Okay, this is the selective use ratio circuit. Okay, and also another technique is selectively use low threshold voltage devices. Okay, and then linkage reductions. Okay, since static power dissipation is caused by the linkage current, so if we reduce the linkage current, so it will also reduce its power dissipations. Okay, so here the linkage reductions can is reduced, okay, by using the stack, okay, stack method. Okay, here I didn't cover more on that. Okay, but this is just for your information on it. Okay, and also body bias and low temperature, so all these I will not discuss further. Okay, I will not discuss further. I cannot discuss more for this one. Okay, because I don't have any materials to explain to you. Okay, you can read yourself. Okay, if you want to know what is all this about. Okay, in designing the CMOS device, okay, we have to consider many things. Okay, if we want to ensure that the device perform well, okay, we have to make sure that it is with low power dissipations, low cost, okay, and also fast switching speed, and also with small delay, okay, many things, okay, that have to consider, okay. And also when we do the considerations, there is some threshold, okay. uh, okay, the threshold here is actually means the balance, okay, balance that have to achieve between the drawback, okay, the negative and the positive, okay. uh, okay, for this one, the threshold, okay, like for example, just now I mentioned the supply voltage, okay, and the power dissipation, okay. The supply voltage cannot be too high. If too high, then it will cause high power dissipation, okay. But the performance will be good. Performance will be good. Okay, if low supply voltage, then it means that it is with low power dissipation, okay, but the performance maybe is not good. Okay, performance is not good here means that the functionality of that device maybe it will not support many function, okay, not support many function, because low supply voltage means that uh, if to perform many functions in the device, the supply voltage must be sufficient, okay. But it is if it is low, the supply voltage is low, then maybe some of the functions cannot be achieved, okay. So here means by this performance not good, okay. So we have to consider which one we want, okay. If we want to achieve low power dissipations, then we have to accept that the performance of that device will not be that good if compared to this that is with the higher power, higher supply voltage, okay. So these are the threshold, what I mean, okay, the threshold that have to consider when we design the CMOS device, okay. Okay, so here you see a diagram here given, good, okay, this is about the quality of the device or the performance of the device, okay. If the device dissipate or consume low power, okay, and also rubbish, that means that it is a good, okay, a good device, okay, and good with it is a rubbish system and with good performance, okay. And then we also have to make sure that the CMOS device can perform very fast, okay, with small delay, and also it is cheap, okay. The cost is not too high, okay. So all these are the elements that have to consider, okay, when we design the CMOS device, okay. So all are important. Okay, design merit of a CMOS circuit. The logic gates are analyzed with respect to several design merit, okay, such as cost, integrity and robustness, performance and energy efficiency, okay. So all these are the evaluations merit, okay, when we want to evaluate an CMOS circuit, okay. Okay, so see this one, this slide is the last for this today presentation. Okay, so I think I have to stop here because I haven't upload other notes to you, okay. I can only cover until here. Okay, and next week I will cover another topic. Okay, later after I reorganize and update all the notes, then only I will upload to you. Okay, so seems like we can end the class now. Okay, before that, any questions from any one of you? Okay, if no questions, then I think we can dismiss class now. Okay, attendance no issue. Okay, I will update later. Okay, okay, so we can dismiss class now. Thank you.